Hello, welcome to video 51 in the lecture Advanced Mathematic Modeling. So in the last video we saw that we can measure the dimension of an object from a power law, because the relation between the number of objects we need and the scale of the object is a power law. So we can just by a double logarithmic plot we can obtain the slope with the dimension as the slope. So the dimension is just a critical exponent, or mathematically we can take it as the limes of the log of n epsilon divided by log of 1 over epsilon. But we need to go on the limits of small epsilons also here, because the scales will never perfectly fit to the borders of our objects. But then we saw already that this concept, this limits to going to infinity, has some problems, because our objects at very small scales, so natural objects, have some internal structure, and then if we go to very small scales, this internal structure is revealed, and then it's not so clear what the dimension, what this measurement will lead us to. And historically now this was found the first time by Richardson, and so we will follow a little bit the findings of Richardson when he was doing this. So we speak about Louis Frey Richardson, and so he was active in different fields. So he was working in hydrodynamic models of weather, but he was also working in quantify conflicts. So quantifying violent conflicts. So basically he was a pacifist, and so he was interested what's the origin of conflicts and war. And here actually he made a very cool discovery. So he made histograms. So he was one of the pioneers to quantify something like this. So here, but how do you quantify the size of the strength of a violent conflict? So you plot their number, a log again of the number of casualties in the conflict, so the number of deaths. And so here we have maybe 1 death, and you can have 10, 100, and so on and so forth, until you have here a huge war, 50 times 10 to 6. So that's the number of casualties. And now we make here log of the frequency, and so here's the log frequency, and then we have a single murder. So we have of course a lot of murder. So somebody was knifed because he was like all the detective stories about this. And here we have a world war. And then we have not so many of these now. So like you could expect that if you have smaller conflicts, we have a lot of more smaller conflicts than larger conflicts. And now if you followed this lecture, you will not be surprised that this follows a power law distribution. And so when he quantified this with all kind of data and made a histogram, so the number of violent conflicts scales as a power law. So the size so the number of violent conflicts scales with size as a power law. So I mean that's of course a pioneering study, and today I mean that's a typical science. Many scientists look at data like this and try to find relations. But Richardson was a pioneer who, for the first time, as far as I know, at least came up with these ideas to find laws in such social data, if you so want. But that's not what I'm. That's not the contribution I'm interested here. But it's now about a different contribution by him, but also related to quantifying violent conflicts. And so he came to the idea: what is the conflict potential? Now speaking about wars. So what's the chance that two countries have war? And then he assumed maybe this has something to do with the borderline between the countries. And now we don't want to go into this if the number or the potential or the likelihood for war really relates to the borderline. But so he came to the idea, let's measure the borderline. And he was interested at first in the conflict between Spain and Portugal. And he wanted to know what's the borderline between the length of the border between Spain and Portugal. And then, so like what you can do, so he took up maps, border, and you take maps, and then you measured the border, and then he found now two different maps, and then one map became to a borderline of this, but then in another map, and that was strange, he came to a borderline of 1214 kilometer. So now you could say, okay, at this time, so he was in the 1960s, maybe the maps were not so okay, so maybe one map was not so precise. But I mean, at this time we could know the height of Mount Everest until very some centimeters, so this cannot be a measurement error in the maps. Geography was too good at this time already, cannot be measurement error. But then what can be the origin of these very different lengths between two maps? And so this became very famous now, not for the borderline between Spain and Portugal, but the borderline, the coast of England. So let's write it down. How long is the coast of Britain? We could have taken any coast, but let's take the coastline of Britain. So now I make a sketch. Okay, so here I tried to make three more or less identical copies of the coastline of Britain. And now the question is, how do you measure the coastline? So first you buy a map, and the map has a certain resolution. And let's say first you have a very rough map of Britain, then not all small coast bytes and things are visible. And let's say we have a map which has a scale of 200 kilometers. And now we want to measure the coastline in this scale. So okay, so we start somewhere here. And now we make our scales. And then we see how many objects do we need. Maybe we have something like this. And you see we need a certain number of objects. Every object has a scale of 200 kilometers. And then we obtain the length. And that's actually what Richardson did here. And then we get a length. And at this scale we say it's maybe 2,400 kilometers. And then, but then he said, okay, maybe that's not so good. So he bought better resolved maps, which has a better resolution of this. And then he had to buy many of them and put them together, probably on the floor of his office. And now he measured the width at the smaller scale. Now he measured at a scale, let's take a scale of 100 kilometers. This means now when we start here, we have already two things here. So we have a scale of this, and we're a bit better. And so our covering of the coastline starts to take more roughness into account, and then, not astonishing, we get a larger length, and then we find a length of 2,800 kilometers. And now we can take an even smaller scale. Take a scale of 50 kilometers and see what we find now. So now maybe I make it like this. So you see we start to be better and better. And we start with the smaller scale to better characterize all the small fjords and so on. And the length again increases. So we get a length of 3,400 kilometers. And then, of course, now the question is, okay, we need better maps and try to find this a little bit better so that we come to the real length of the coastline. Yeah, and that's what Richardson was doing. Okay. Okay, so maybe let's write this more systematically. So calculate length, or measure the length of coastline at different scales. And let's plot then the resulting length. And then we say the length that we obtain at a certain scale equals the number of scales we need times the scale. Right, and this is what we found here. Depending on the scale we use, we have a different length. And so we can make a plot. And have here our scale, and have here the lengths at this scale. And then we took the large scale of this 200 kilometer, and we had a length of 2,400 kilometer. and then we halved the scale, and then we had a bit larger length. Then we halved the scale again, and when we had a larger scale, a larger length. And now the thing is, so we can take something into between here, we get such something like this. So the smaller the scale, the more resolution we obtain, and the larger the our estimate or measurement of the coastline length is like this. And now the natural idea would be, okay, but that's the true length, and then hopefully if we follow this line, and if we now only make our scale smaller enough, we should come eventually to the right length of the coastline. Yeah? I mean, that was all the intuitive expectation. But then the thing is, if we now take not only 50 kilometers, so this was here the 50 kilometer, it was a 200 kilometer. Now let's take the 25 kilometer. It turned out, oh, the length is like this. And if we now take a smaller, let's say 10 kilometer, the length is even larger. And so that was what Richardson found, that we have here a divergence. So this curve never settles to a typical length, but for every scale that we use, we get a different length, and when the scales go to 0, the length goes to infinity. So, and that was the observation by Richardson. That length, call it 0. So the limes epsilon goes to 0 of n epsilon times epsilon is infinite. So this means the length of a coastline does not exist, is not defined. So the length, so if you take the US coast, or the coast of Britain, or you could take any other country, and you want to know what's the length of this, that's a question which doesn't have an answer, because the length depends on the scale that you use to measure the object. Yeah. So the length of the coastline does not exist in itself. It depends on the scale of measurement. And this is really fundamental, this observation here, because this destroys all our ideas of our Euclidean geometry. Because if we would do the same thing for a normal square or for a cube or something, or for a line for a circle, this would converge to a certain length. I mean, that's what we showed before. That's how we can, I mean, before we showed the measurement of dimensions, but if you would now measure the length of something, you would then saturate. Yeah? But the fact that for a natural object such a length does not exist, this means the coastline of Britain is not an object of our Euclidean geometry. Yeah. So it means it's something different. It's not something you learn in elementary geometry in school. And so what it actually is, it's a fractal, and we will come to this. But So now to store again, you would directly say when you see a graph like this, let's plot these results on a double logarithmic scale. And indeed, when we plot this at a log-log scale, log epsilon, logarithm of our length, then this follows here on a straight line. Something and we know if you have power law, then of course if you would plot it in linear scales, then the power law diverges for epsilon goes to 0. Yeah? So we have again the power law, and so we have a power law. We see that the length is a function of epsilon, and this goes as the scale to a critical exponent rho, and this we call nowadays the Richardson exponent. And so this is a measure for the roughness of the coastline. And now you can take other coastlines. So that was here Britain. And now take another coastline, for example Portugal. That was the coastline here Richardson was first interested. We have again a power law, but with a different exponent. We have Germany, it's not so rough. It's Germany. And then you have some coastlines which actually behave like a normal geometric objects. For example, that's south, so that's here, Germany. Portugal. And this here is South Africa. And coastlines which have here such a roughness of 0. These are typical coastlines which were not, which didn't emerge naturally, but these are coastlines which were taken, decided by politicians who just said, okay, beyond this latitude, that's the border of the country, and if you just divide a country, the size of the border of a country by political decisions, then you end up with a very smooth border, and then you have a Richardson exponent like 0. But if you have rough coastlines, in particular if this like Norway or something where you have a lot of fjords, when it's really the geographical borders, you have very rough surfaces here. And so at this time, these findings of Richardson at this time were too advanced for his time. And so they were forgotten, more or less. And then it took later the genius of Benoit Mandelbrot and so this was then in 1967. He rediscovered this finding from Richardson, and he exploited this in much detail, and then he coined the notion of a fractal. Such objects are fractals. Yeah? So a fractal is an object which has a Richardson exponent with rho not equal 0. And so let's summarize this a little bit. So the roughness, the Richardson exponent, is a number which is typically larger than 1, and if fractal is different than 1, because so the Richardson exponent is smaller than 1, and no, it was correct. So like, and for an object of the normal geometry, so object of Euclidean geometry, of like a linear a straight line, so we have a roughness exponent of 0. That would be South Africa. Now if we take coastline of Britain, we have a roughness of 0.22 about. If we take the coastline of Portugal, we have a roughness of 0.52, so the roughness of Portugal is a bit larger, and so we can say that instead of the length of a coastline, at least we can quantify the roughness by this Richardson exponent. And so what does the roughness mean? If we have, for example, a rho of 0.2, this means a doubling of the scale. This means the length is changed by 25%. And now we can say something like this. So if we have a straight line or one-dimensional object or a smooth line, so this would have a roughness of 0. Now let's take, we have an object which has these fjords. Then we have a larger roughness. And now we have the limit, and we will see this limit soon. If we go to r equal 1, we have a space-filling curve. We have a curve which is so rough that it basically fills the whole area. So that's a space-filling curve. So that means this roughness exponent tells us where we lie in this continuum of a very smooth curve to the maximal of a space-filling curve. But this we will see in the next video, where we also see how this power law here is now related to the power law we had before, where we looked for our definition of the dimension, how the number of objects scales with epsilon. So seemingly these things are related, and so let's see what is the dimension of such a rough object. But this we will do in the next video.